Okay, so we are going to do a few problems on basic mechanics of materials concepts, basic concepts of stress and strain and elastic modulus. So here is a very simple question. A cylindrical rod, 20 millimeter in diameter, is pulled with a force of 10 kilonewton. The bar is 1 meter long. The picture is shown here. The material has an elastic modulus of 100 gigapascal, Poisson's ratio of 0.25. Determine the change in length and change in diameter of the rod. So what is given? The size of the rod, the diameter is given, the force is given, right? From the force and the diameter. So what are we going to do first? Force and diameter is given, you can easily find the stress, correct? So stress is force over area, and the force is 10 kilonewton, which is 10 times 10,000 Newton divided by 20 millimeter diameter. So area is pi times d square, 20 times 20 over 4. And if you do that, you will get a stress of 31.83 newtons per millimeter square. Make sure that you're consistent in your units. So you will get 31.83 newtons per millimeter square, which is the same. Newtons per millimeter square is the same as megapascal. Now, you know the stress. What you also know is stress is equal to elastic modulus times the longitudinal strain, right? I'm going to use a symbol here for strain. So stress is equal to elastic modulus times longitudinal strain. Elastic modulus is known, 100 gigapascal. Therefore, you can find longitudinal strain is equal to stress divided by elastic modulus. Stress is 31.83 newtons per millimeter square is megapascal, divided by elastic modulus, right? Oops. So, strain is stress divided by elastic modulus. 100 GPa is 100 times 1000 MPa, so that we are consistent in our units. And that will give you a strain of longitudinal strain of 0.000318. So this is your longitudinal strain that you have in this specimen. So this is your longitudinal strain. Once you know this longitudinal strain, what are you asked? Change in length, right? So change in length, which we used to call delta L, is nothing but longitudinal strain times length, right? All of you remember this. So change in length, because longitudinal strain is change in length over original length. Therefore, change in length is equal to longitudinal strain times length, which when you do it, 0.000318 times what is the length of the bar? 1 meter, which is 1000 millimeters, which will give you change in length is 0.318 millimeters, right? So this is your first part of your answer to first part of your question, 0.318 millimeters. So now, what is the next part of the question? The next part of the question asks you, what is the change in diameter of the rod? Now, for change in diameter of the rod, you need the lateral strain, correct? Because lateral strain is where the diameter of the rod comes into picture. Now, remember, this is pulled in tension, right? So what you're seeing is this rod is being pulled in tension which means its length is going to increase and diameter is going to decrease. Therefore, if I start to look at the Poisson's ratio, which is given to you, Poisson's ratio, which is nothing but the ratio of lateral strain to longitudinal strain, right? So it is the ratio of lateral strain to the longitudinal strain. That's how we have defined Poisson's ratio. So it's the ratio of lateral strain to longitudinal strain. We put in a negative sign also because when longitudinal strain is positive, remember this is a positive strain, correct? Because the length is increasing. So I'll put in a positive here just to show that the length is increasing when I pull with a tensile force. So that's positive. Now, what is lateral strain? Lateral strain is simply change in diameter over original diameter. So I can write lateral strain. Again, these are all definitions that we have done. So lateral strain is equal to change in diameter over the original diameter. We don't know change in diameter, but what we know is given Poisson's ratio and longitudinal strain, you can find lateral strain. So lateral strain is also equal to, from this equation, Poisson's ratio times longitudinal strain. So if you look at this equation here, lateral strain is equal to Poisson's ratio times longitudinal strain. So I do that. What is Poisson's ratio? Given as 0.25 times my longitudinal strain, which is from here, 0.000318. If I do that, I will get it as 7.95 times 10 to the minus 5. Again, it's a strain. So remember that there is no unit because it's a strain. So this is your lateral strain. 7.95 times 10 to the minus 5 is a lateral strain. Remember, when you're pulling down, length is increasing. So the cylinder is actually getting thinner. Therefore, this will be a negative value, right? Because the length is, the diameter is reducing. So I will put that as a negative value here. So lateral strain is known. So when the lateral strain is known, you can simply say change in diameter is equal to lateral strain times the initial or original diameter times the original diameter, which is equal to 7.95 times 10 to the minus 5 times original diameter is 20 mm, which will give you 0.0015. That is your change in diameter of the specimen under this load. Since the force is tensile, the length will increase and the diameter will decrease. Therefore, this would be a reduction in diameter. I will just put in a minus sign there just to make sure that it is a reduction in diameter. So I hope it's clear to all of you. Okay. So this is a very simple problem. Now let's do another problem. Erase everything. So the next problem is a problem on a prismatic specimen with a square cross section. The last problem was cylindrical. This is square, side length of 10 millimeters. So this square has a side length of 10 millimeter. So this is 10 millimeter. This also is 10 millimeter because it's a square cross section. 10 and a length of 100 mm. It is subjected to a compressive force of 30 kilonewton along its axis. If the specimen changes its length by 0.1 millimeter. Remember, it is compression, therefore the length is going to go down. So your change in length is given as 0.1 millimeter, right? I can straight away write that is negative because my length has gone down. Change in length is 0.1 millimeter and the side length is 10 millimeter. Dimensional sides change by 0.003. Change in side length is 0.003 mm, right? When I'm squishing it, the cross-sectional area increases. Therefore, change in the side length increases. I can then now write that as positive. Okay, now what do I need to find out? I need to find out the elastic modulus and Poisson's ratio of this material. So elastic modulus is nothing but the ratio of stress over longitudinal strain, correct? So can you find the stress and can you find the longitudinal strain? Because elastic modulus is stress over, I'm going to carry over from my previous symbol, stress over longitudinal strain. Stress is nothing but force over area. Force is given as 30 kilonewton. Side length is 10 mm. Therefore, doesn't require me to do too much of calculations here. Stress is simply 30 kilonewton is 30,000 newtons. Make sure that you correct the units. You do the right units so that you're not messing up that. Divide by area. Square cross section, 10 millimeter side. So 10 by 10 millimeter square is my area. And I will get a stress of 300 newtons per millimeter square or 300 megapascal. So 300 megapascal is my stress in this case. Elastic modulus is given. No, I have to find the elastic modulus. So I now have to find the longitudinal strain. So longitudinal strain would be change in length over original length. I have put change in length earlier as 0.1 millimeters. That is change in length. And original length is 100 millimeters for the sample. Therefore, my strain would be 0.001. I'm going to put in a negative sign because it's compression. My longitudinal strain is negative or the length has actually gone down because it's a compressive force, right? So I now know my longitudinal strain. I know my stress, I know my longitudinal strain. Therefore, elastic modulus is nothing but stress over longitudinal strain, which is 300 megapascal divided by 0.001, which is 300,000 megapascal, which is equal to 300 gigapascal. Correct? So this is my elastic modulus. 300 gigapascal is my elastic modulus. So very straightforward, simple calculation. Now, the next question is what's my Poisson's ratio? So you can use a symbol for Poisson's ratio. I'm not using it because it's easy to write in a PowerPoint slide, but make sure that when you're doing your problems, you use the symbols. So Poisson's ratio like we did in the last slide, is nothing but change in the lateral strain over longitudinal strain, a negative sign so that the Poisson's ratio always remains positive. Now, what do you know? You know longitudinal strain. What you need is lateral strain. But that's not a difficult thing, because I know my change in the length of the side also. So lateral strain is equal to change in side length over the original side length. So what is change in side length? Given as 0.003 divided by my original side length is 10 millimeters, correct? So 0.003 by 10, which is 0.0003. Is it positive or negative? When you're squishing, the sides are increasing. Therefore, the lateral strain is positive. 0.0003 positive. That lateral strain, now Poisson's ratio is simply this ratio, which is equal to minus, what is my lateral strain? Plus 0.0003 divided by, what is my longitudinal strain? Minus 0.001. You will get a Poisson's ratio of 0.30. Right, so if calculated. Now, to check if your Poisson's ratio is correct, you should always get a Poisson's ratio between 0 and 0.5. For most engineering materials that we deal with, your Poisson's ratio would be anywhere between 0.15 and 0.4. That is your check. If your Poisson's ratio is 2 or 3, you're wrong. If your Poisson's ratio is 0.001, 0.002, very, very small numbers, you're wrong. You generally will have Poisson's ratio for general materials between, say, 0.1 to 0.5. So that is a check that you can do to make sure that you are correct. So those are two problems that we did. Let's do a next problem. So here, it is a problem that gives you, that doesn't give you the cross-sectional dimensions, but just tells you that a cross-section and a length for a prismatic specimen, you're stretching with a force of 10 kilonewton. So when you say stretching, it is tensile stress, 10 kilonewton in its elastic range. Longitudinal strain is given, elastic modulus is given, what is the side length of your specimen. So very, very simple problem. Your strain is given, elastic modulus is given, force is given, right? What is the side length of the specimen cross section? You're asked to find the value of A, right? So A is the cross-sectional dimension, therefore cross-sectional area, because it's a square cross-section, is equal to A square, correct? And the stress in the specimen is force over area. Force is 10 kilonewton, which is 10,000 Newton divided by A square. Now, what is the other definition for stress? Stress is also equal to elastic modulus times longitudinal strain, correct? Elastic modulus times longitudinal strain. So stress is also elastic modulus times longitudinal strain. Now, do I have both the values? Yes, I'm given the longitudinal strain, I'm given the elastic modulus. Therefore, I can find the stress, which is equal to 100 GPa, 1 gigapascal is 1000 megapascal. So 100,000 megapascal, 1 megapascal is 1 Newton per millimeter square, so that everything is in newtons and millimeters. So you will never get confused with the units. So 100 gigapascal is 100,000 megapascal or 100,000 Newton per millimeter square times, what's your strain? 0.002, correct? So you will find that your stress is equal to 200 megapascals or 200 Newton per millimeter square. So this is your stress. Now, what is that? That is equal to 10,000 Newton over A square, correct? So you can equate both of those. So you can say that 10,000 Newtons over A square is equal to 200 Newtons per millimeter square. Therefore, A square will be in millimeter square. We can do the simplification. A square or the area is equal to 50 millimeter square, right? 10,000 divided by 200. 50 millimeter square. If A square is 50 millimeter square, the side length A is equal to 7.07 millimeters. That is how you calculate the side length of this prismatic specimen. Okay, so I'm hoping that these simple problems you're able to understand. Please work out such problems. Look at the worked out examples. Look at lots of example problems that you can see in several books. Create your own problems. It'll be easy to do. Okay, and then the final problem in this set that we are going to look at is a bending problem. A simply supported beam is 50 millimeter wide and 100 millimeter deep. So the cross section is 50 millimeter wide and 100 millimeter deep. So cross section is, if you cut this and look here, that's what you see. That's your cross section, right? That's a cross section. So whatever is here, that is 50 millimeter by 100 millimeters. And it has a span of 1 meter. Span of a beam is the distance between the supports of the beam. So this beam, simply supported beam, has 2 supports. The span is the distance between supports. 1 meter is a span. It is subjected to a uniformly distributed load of 10 kilonewtons per meter. So in this beam, there is a uniformly distributed load of 10 kilonewtons per meter. If the material that the beam is made of has a tensile strength of 12.5 megapascal, will the beam crack under the imposed load? The question is, will the beam crack? Now, if you want to know if the beam will crack or will not crack, you have to find what is the stress in the beam. What is the maximum stress in the beam? You are given the strength of the beam, right? What is the capacity of the beam is given to you. You need to find out what is the stress in the beam under this given loading. So I'm hoping that you know how to calculate bending moments. If you want to draw the bending moment diagram, you can do that. Shear and bending moment diagrams, you can do that. But I would advise you to know the equations for bending moments and shear forces for simple loading cases. This is a uniformly distributed loading case. It's a simply supported beam. You should be able to write M as WL square over 8. Where L is a span, W is the load per unit length, which is given as 10 kilonewton per meter. So 10 kilonewtons is 10,000 Newton. So 10,000 Newton per meter times L is 1 meter. So 1 square, 1 meter square, right? WL square. I'm assuming that you know the derivation for all of those, divided by 8, right? So you will get 10,000 times 1 square over 8, which is, let me do the calculations quickly, 10,000 over 8, 1,250, 1,250 Newton meter, correct? Newton meter, which is equal to 1,250 times 1,000 Newton millimeters. So everything is in newtons and millimeters so that we are consistent in our units. So this is the moment or the maximum moment in this beam. When you draw the bending moment diagram, you will know what shape the maximum moment is. And in such a loading condition, the maximum moment is going to be at the midspan of the beam. You would have known that from the derivations that you have done in deformable solids class. If not, you will do more of this in structural analysis. You should remember that. So that is the moment 1250 times 10 to the 3 Newton millimeter. That's your moment. Now, what's your maximum stress? Sigma max, I'm not going to write sigma max, I'm going to write maximum stress, is equal to the moment times the distance from the centroidal axis to the extreme tension fiber divided by moment of inertia. So for bending, pure bending, you should have derived this equation in your deformable solids class. You should have known how to derive this equation. So maximum stress in a simply supported beam that is subjected to a uniformly distributed load. In this case, whatever be the loading condition, maximum stress is equal to MC over I if it is pure bending. M, the bending moment, we have just calculated here as WL square over 8. C, now if you look at this beam is going to bend like this, right? It's going to bend like this. And in a beam that's bending like this, the maximum tensile stress is going to be here on the bottom part of the beam. Because the moment is maximum at the midspan, the maximum tensile stress also will be here. So let's calculate what that is. Therefore, because it is a midspan, C is basically the distance from extreme tension fiber to the centroid of the cross section. Because it's a rectangular section, you can see that C will be 100 over 2 or 50, right? And then, of course, moment of inertia I for a rectangular beam. It's moment of inertia because the beam is bending like this. And if you look at the bending axis, the beam is bending like this. So this is the axis of bending, correct? And if you look at the cross section, that axis of bending passes through this. Therefore, the moment of inertia is B d cube over 12. You should have done the derivations for this in your deformable solids class. You should be able to calculate the moments of inertia, centroids and moments of inertia of a lot of different types of sections that you need. But simply, you should also know that for a rectangular section, the moment of inertia is of about its own centroidal axis. Again, moment of inertia is different based on where you take the moment of inertia. Here we are taking it about its own centroidal axis. It's B d cube over 12. B is 50 millimeters, right? So this is 50, that is D 100. So 50 times 100 cube over 12, that's your moment of inertia. And C for this center, for this cross section, is equal to 50 millimeters because it is the midpoint of the cross section. Therefore, if you do all this, you will find that the maximum stress moment is 1250,000 Newton millimeter times C is 50 millimeter over I is whatever this number, BD cube over 12. I'll put that in square brackets so that you don't miss it. You will get a maximum stress as 15 megapascal, 15 newtons per millimeter square, which is equal to 15 megapascal. This is your maximum stress that you're getting in this beam at this location, which is the maximum stress. Now, the beam has a tensile strength of 12.5, right? The beam can carry tensile strength, or the beam can carry a maximum stress of 12.5 MPa. Whatever you have imposed is 15, which is greater than 12. Therefore, since the imposed stress that you've calculated is greater than tensile strength, the beam will crack. If the value that you got here, maximum stress that you got here is lower than the strength, it will not crack. If the value that you got, if the calculated stress is higher than the strength, you will crack. So this is another way in which you can look at a bending problem. So what we have done are problems that deals with straight axial loading, both compression and tension, calculating elastic modulus, Poisson's ratio, dimensions, all of that. So within the three problems that you have done in the first three problems, lots of that class of problems have been solved. So look for similar problems and try solving them. And this is a bending problem that we have done. So between these three or these four problems, you should have a reasonably good handle on all these kinds of problems.